Okay, welcome to this video on plate tectonics. Well, before we get started, first let's think about why do we care about plate tectonics? Well, so first of all, plate tectonics gives us fantastic landscapes like we see in this picture right here. This is a view of the Himalayan mountain range poking up through the clouds. And the formation of the Himalayas is directly tied to plate tectonics. Aside from these uh, in addition to caring about how landscapes like this form, in addition to explaining how landscapes like this form, plate tectonics can also help us understand something about natural hazards. So for example, this is a building that collapsed during the 1989 Loma Prieta earthquake that hit the Bay Area. This particular building that collapsed is in San Francisco. So of course that has direct ties to plate tectonics. Earthquakes can also trigger tsunamis, like this tsunami we see here hitting Japan during their 2011 earthquake. And plate tectonics can also be responsible for landslides. So of course, landslides happen in steep landscapes, and you need plate tectonics to create steep landscapes. And earthquakes can also trigger landslides. So for example, this is a landslide that was triggered during an earthquake in Japan. So lots of important and interesting reasons for understanding plate tectonics. The surface of the Earth's crust, is divided up into 13 major plates and a bunch of smaller ones. And these plates, of course, aren't static. They move around. So for example, the North American plate is moving in this direction relative to the Eurasian plate. Same thing, the African plate is pulling away in this direction relative to the South American plate. The Pacific plate is heading off to the northwest relative to the North American plate, like that. And so all these plates are moving around. They interact in all sorts of interesting ways. And that's how we get things like earthquakes and volcanoes. There are three main types of plate boundaries. One of the three types of plate boundaries is the divergent plate boundary, which we can see here. Now notice first that each of these plates has both oceanic crust and continental crust attached to it. So now in a divergent plate boundary, plates move away from each other. So that plate's moving in that direction, and this plate is moving in that direction. Now, as a result, a gap forms in the crust, and this gap relieves pressure, and that allows magma to form, to rise up into that gap. So this is all magma that's forming. And that magma rises up and produces lava flows that come out onto the ocean floor. Now at the same time, some of that magma cools and hardens right along the edge of the plate, which is a good thing because otherwise, as these plates keep pulling apart from each other, this gap would get bigger and bigger. And so what happens is that magma essentially helps to close that gap a little bit. But of course, the gap is always open because these plates are pulling apart from each other. Now, another consequence of magma formation is that because this area is hot, the crust is lighter, it's more buoyant, and you can see that it actually rises up a little bit. So there's a little bit of uh, um, rising up here on the edges of the crust, and that leads to what's called a mid-ocean ridge. So it's literally a ridge that's underneath the ocean. Now, a good example of a mid-ocean ridge is the one between Africa, which is pulling off towards the east, and South America, which is pulling off towards the west. Now, the good thing about this type of plate boundary is that it has relatively mild earthquakes. So this is not a plate boundary that is associated with significant natural hazards. So here's an example. This is the Mid-Atlantic Ridge, what I'm tracing out here in the dashed red line. And you can see from this picture that it's literally a ridge. It's an underwater ridge. And it's formed because Africa and Europe are pulling off in that direction. South America is heading off in this direction, and so is North America. Okay, so that's a divergent plate boundary, and this one in particular is called the Mid-Atlantic Atlantic Ridge. Okay, the second type of plate boundary is the convergent plate boundary. A classic example of this is the Indian plate sliding northward like this, running into the Tibetan plate and actually sliding underneath it. So the Tibetan plate is riding up over the Indian plate. And as a result, where these two plates overlap, as you can imagine, you get an area of high elevation because the crust is essentially twice as thick. And in fact, this is where we see the Himalayas, right where the India is sliding underneath Tibet. Now, in terms of natural hazards, this type of plate boundary is fairly dangerous, as these types of collisions lead to relatively big earthquakes. Now, convergent plate boundaries come in three flavors. So the first one is the one that we just saw right here, where you have two continents colliding. And just to see what this looks like, here we have India, the bottom, moving towards the north, relative to Tibet, which is moving towards the south. So the Indian subcontinent is plowing underneath Tibet, and then we can see the Himalayas right here, right along the edge of that collision. Now, another type of convergent plate boundary is where you have an oceanic crust smashing into continental crust. So here on the left, we have the oceanic crust going this way relative to the continental crust, which is going in this direction. And as we saw before, as the oceanic crust dives down, and it's diving down because it's denser than the continental crust, the crust begins to melt, and this is facilitated by the fact that the oceanic crust is saturated with water. So we've got magma forming. This magma, because it's hot and it's buoyant, rises up through the continental crust, and you'll remember in some cases some of that magma cools within the crust to form plutonic rocks, and some of that magma reaches up to the surface to erupt out of volcanoes. So here's some lava flowing down the side of this volcano. Now, of course, as you can imagine, these types of collisions are associated with volcanic hazards. But they're also associated with earthquakes. And those earthquakes tend to form or tend to begin right about there. So they're relatively deep. But they're also quite powerful. And in fact, they're so strong that they're also associated with tsunamis. So a lot going on where we have ocean to continent plate collisions. You have volcanic hazards, you have deep and powerful earthquakes, and then you can also have tsunamis. We have one of these types of plate boundaries just to the north of us. This is an oceanic plate right here. And you can see that it's moving in this direction and it's diving underneath North America. So just to get you situated, this is the Sacramento Valley down here. You can see Mount Shasta right there. So Mount Shasta is a volcano formed by this oceanic plate diving underneath Northern California. And then if you're familiar with Crater Lake up in Oregon, that's also a consequence of this plate subducting underneath North America. And in fact, there's just a chain of volcanoes. These are all volcanoes formed as a result of this plate boundary. And so where you have one plate diving underneath another plate, that's known as a subduction zone. So all of this through here, the dashed line, this is a big subduction zone. And finally, the third type of convergent plate boundary is where you have oceanic crust colliding with other oceanic crust. So here we have this plate in this direction, slamming into this plate right here. And again, as we saw before, where you have oceanic plate subducting, it melts, magma forms, and that magma rises up to form volcanoes. So this is lava coming out of the volcano. Now, because it's two oceanic plates, this actually just forms a volcanic island. And in fact, as I'll show you, it's not just one island, it's a chain of islands. And so the technical term for this chain of volcanic islands is a volcanic island arc. Now, this also leads to strong and deep earthquakes. And those earthquakes can generate deadly tsunamis. So here's the island of Japan. So this is a classic situation that we get in a subduction zone between two bits of oceanic crust. That crust is moving in that direction. This plate is moving in this direction. This is the subduction zone right here. And then you see a chain of volcanoes forming as this crust right here, as it moves underneath the other crust, begins to melt and form magma. So, of course, one of the classic volcanoes in Japan is Mount Fuji, and that's formed by this subducting process. And the final type of plate boundary is a transform plate boundary. As you can see, we're looking at the Bay Area. So here's the Bay right there. Here's San Jose right here. And as I'm sure most of you are aware, we have the San Andreas Fault right in our backyard. So the yellow line here is the San Andreas Fault. So that's a transform plate boundary. And a transform plate boundary is characterized by having two plates sliding past each other. So the Pacific plate is sliding up in this direction. The North American plate is sliding in this direction. And so, for example, if you decide to spend the day, if you live in San Jose and you decide to spend the day in Santa Cruz, which is right here, you're crossing over this plate boundary and you're spending the day on an entirely different tectonic plate. So that's just something to think about as you're driving over the mountains and driving to the coast. You're actually moving to a completely different tectonic plate. Now, as we know, this type of plate boundary is associated with strong and shallow earthquakes. And so the fact that these earthquakes are shallow means that we feel them a lot more. They're much closer to the surface where we live. Okay, well, thank you for your attention. I hope that was helpful.